Number 1. Dan is investing $750 in an account with a nominal yearly rate of 5.2% that compounds continuously. Write a function for f of t, the future value of the account after t years. So the minute you see compounding continuously, you need to be thinking of PERT. You need to be thinking of PE to the RT, where E is that Euler's number 2.718281828459545. That's that number that's in our calculator. It's irrational like pi, but E is that number that has to deal with compounding continuously. So we know that f of t equals, well, p is our principal. We started with 750. E is a number. I know it's weird. E is a number to the r. Well, I don't like 5.2%. 5.2% is 0.052. 0.052. So 0.052 to the times t. That's our future value function when we're compounding continuously. So how much money does Dan have after 9 years? Well, what do I do with 9? Plug it in. F of 9 is 750 e to the 0.052 times 9. So if I go to my calculator, 750, e's in two places. I like using the one above the division. E raised to the 0.052 times 9. So how much money is Dan going to have? Well, $1,197, and we look at the third place. I'm going to round up. So 59 rounds up to 60. So 1197, 60. 1197, 60. That's how much money Dan will have after 9 years. $1,197.60. Using your calculator, approximate how many years it takes to double his investment. Explain how you arrived at your answer. So Dan's starting with 750. If I want to double that, 750 times 2 is I want to know when it gets to 1500. When does 1500 equal 750 e to the 0.052 t? There's a couple ways to do this. I think the easiest way is to graph it. In y1, we can put 1500. In y2, we can put that other function, 750 e to the 0.052 x. In y1, I put this side of the equation. In y2, I put the second side of the equation. And I want to know where these two intersect. If we graph it, we might not see much. And we probably won't. Because my y values go up to 1500. So let's change our y max so we can actually see this. Well, I want 1500, so let's go to 2000. And now let's hit graph. There's the exponential function. And where's the other? I have an extra 0 here. That'd be very helpful to not have an extra 0. So I want to know, oh, I don't see it. They intersect somewhere over there. So if I want to see it, I have to change my x-axis scale. So it's past 10, so maybe we go to 20. Maybe we go to 20 and see if we can see it there. Aha, that's where they intersect. So second trace, intersect. Move Mr. Blinky close to where they intersect. I have to hit it a bunch of times. I can't hold it down like you can. I probably went too far, but that's okay. Stop. No, too far. Oh, pretty close. Enter 3 times. How many years does it take? About 13.3. So it takes about 13.3 years. I just round to the nearest 10th, because that's the x value of where they intersect. You could also do this by looking at your table and looking at, well, where are these two about the same? So looking at my y values to figure out when they're about the same. And 12's not enough. 13's not. 15 is. 14 is. So it's somewhere between 13 and 14, which makes sense. So it could have been a clue to tell me where to look. By looking at my tables, it's going to hit sometimes between 13 and 14. It appears to be about 13.3. Determine the effective annual rate of the account. Well, right now we have, as our function, if I slid back a page, f of t equals 750 e to the point of 0.052 to the t. So we know that's our principal amount. What determines the rate is this expression right here. E to the point 0.052 determines the rate at which this is happening at. So we could use the power to a power rule to say that this is the rate. E to the point 0.052 is the 1 plus r. So that's going to tell us what the rate is. E to the point 0.052 is the rate. So let's type that in. To reset your window, what you're going to want to do, you're going to hit Zoom Standard. Zoom 6 brings you back to where you want to be. Unrelated, so I want to figure out what's E, the number E to 0.052. This is going to tell me 1 plus my rate. That's 1 plus my rate because it's exponential growth. So 1 plus r equals, well, what did it equal? 1.05337. Let's write that down. 1.05337, about. Well, the 1 doesn't matter, so r equals 0.05337. What's the actual percentage? 5.337%-ish. Notice that that's actually larger than the 5.2% that we started with. The effective rate, because we're compounding continuously, is 5.337%. If I did 5.337% compounding annually, that would give me the same effect as compounding continuously at 5.2%. So it's just using that power of a power rule to figure out, well, that e to the 0.052, that tells me the effective rate. That was lesson 8, short and sweet. I'm assuming you enjoyed that.